Hello, we are
Tanvi
and Sheilla, the Math Decoders.
We're so excited to teach you about Newton's method and linearization.
Let's dive right into it.
So, derivatives are often correlated with the tangent line to the curve at a point. This tangent line is very important because it provides a useful representation of the curve.
A differentiable curve is a continuous function whose derivative exists at all points on its domain. This curve is always locally linear.
If the function is differentiable at x equals a, then the equation of the tangent line, L of x equals f of a plus f prime of a times x minus a, defines the linearization of f at a.
The approximation of f of x, which we can call L of x, is the standard linear approximation of f at a. Essentially, linear approximation just means that if we zoom into the curve close enough, we will see a line.
Now that you've learned some basics about linearization, let's practice!
For the next two problems, we're asked to find the linearization L of x of f of x at x is equal to a. Remember, L of x is equal to f of a plus f prime of a times x minus a.
Our first equation is x cubed minus 2x plus 3 at a equals 2. First, we will plug in 2 into the original equation to get 7. Next, we will take the derivative of the original equation, which is 3x squared minus 2. After, we will plug in 2 into the derivative equation to get 10. Next, we will plug in these values into the linearization or tangent line equation, which is L of x equals f of a, which is our 7, plus f prime of a, which is our 10, times x minus a, which is x minus 2. That simplifies to L of x equals 10x minus 13.
For number 2, we are asked to find the linearization of tan x at a is equal to pi. Firstly, we plug pi into the original equation, which is tan of pi, which is 0. Then, we find the derivative of tan x, which is secant squared x. After that, we plug pi into the derivative equation and get secant squared of pi, which is equal to 1. Finally, we plug all of this into the L of x equation, and we get 0 plus 1 times x minus pi. When we simplify, our final product is x minus pi. The cool thing about the L of x formula is that we can actually use it to approximate root problems. This is especially true for when we are trying to find the root of a number that is not a perfect cube, square, etc.
For example, if we are trying to find the square root of 101, but we don't have a calculator, we can simply plug it into the equation of a tangent line and use the closest perfect square to 101, because that just means that our approximation will be very close to 101 on its graph.
Let's show you!
So our question is the square root of 101, and we're going to find the approximate root to this question by using the linearization or tangent line equation. Our a in that equation is going to be 100 because it's the closest perfect square to 101, and our x is going to be 101 because that's what we're trying to find. So to do this, we're going to do f of a equals square root of a, which is what we're trying to find. A is going to be 100, and the square root of 100 is going to be equal to 10. Next, we will find the derivative of this exact equation, which is going to be 1/2 a to the negative 1/2. We will plug in 100 to a here again, and we'll get 0.05. Next, we'll plug in all these values into the linearization / tangent line equation. Then we get 10, which is our f of a, plus 0.05, which is our f prime of a, times x minus a, which is 101 minus 100, which equals 10.05.
Next, we're asked to find the cube root of 998. The closest perfect cube to 998 is 1000, which we will make our a. So first, we're going to find f of a, which is a cube root of a. The cube root of 1000 is equal to 10. Next, we're going to find the derivative of f of a, which is 1/3 times a to the negative 2/3. When we plug 1000 into the derivative equation, we get 1 over 300. Finally, we're going to plug all of these values into the L of x equation. So we get 10, which is f of a, plus 1 over 300, which is f prime of a, times 998 minus 1000. We end up getting 9.9933. Let's move into approximating binomial power problems. The nice thing about approximating binomial powers is that you can solve any equation for y that comes in this form. Y equals 1 plus x to the k using this formula. Y is equal to 1 plus kx.
Essentially, you just have to reorder your values, and you'll have your answer. Also, it gives you a pretty exact value versus just a rough approximation. But this method is only designed specifically for x values that are very close to 0.
Hey Tanvi, what time is it?
Practice time!
So, for the next two questions, we are asked to use linear approximation, which states that 1 plus x to the k is approximately equal to 1 plus kx, to find an approximation for f of x for values of x that are near 0.
So this equation is f of x equals 1 minus x to the sixth. K equals 6 in this equation, so all we have to do is put it into 1 plus kx. So it would be 1 minus 6, which is our k, times x.
This next problem is f of x is equal to the cube root of 1 minus 1 over 2 plus x squared. This may look complicated, but trust us, it's not. So, the first thing that we're doing is reordering the exponents to make it equal to 2/3. So it's going to be 1 minus 1 over 2 plus x to the 2/3. Then, all we need to do is bring the 2/3 in front because it's equal to k. So it'll become 1 minus 2/3 times 1 over 2 plus x. Then we just need to simplify and distribute, and our final product is 1 minus 2 over 6 plus 3x. Now, Tanvi and I think that you are very ready for Newton's method. Newton's method will help you with accurately approximating a zero of a function with the zeros of its tangent lines, or linearizations. First, you will need to graph the function and find an approximation of the x-intercept. Life hack: to find the best approximation, you can actually use your graphing calculator or Desmos.
As you can see, the more tangent lines you have, the closer you will be to the actual root. So to find the x-intercept of each tangent line, we use this formula. X sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n. X sub n is our first guess. F of x sub n is our guess plugged into the original function, and f prime of x sub n is our guess plugged into the derivative function.
When you get the answer, you just plug it back into the original formula as your second guess and keep calculating it until your result is really close to the actual root that you're looking for.
So, for the next two problems, we will be using Newton's method to estimate all real solutions of the equation. We will be rounding to 6 decimal places. So, the first question is x cubed plus x minus 1 equals 0. And our first approximation or guess is 0.6823, which we found using Desmos by graphing this equation onto the app. After that, we found f of 0.6823 divided by f prime of 0.6823. So, we plug in 0.6823 into our original equation to get negative 6.663 times 10 to the negative fifth. Next, we found the derivative equation of the original equation, which was 3x squared plus 1. We plugged in 0.6823 into this equation to get 2.396. We then divided both of those values up, the original and the derivative, and then we subtracted it by 0.6823, which gave us 0.682272. That is our second guess, and we'll be using that for the third guess. Next, we found f of 0.682272, and then we also divided that by f prime of 0.682272. So, to find the answer of the original equation, we did f of 0.682272, and that gave us negative 1.337 times 10 to the negative fourth, and then we found f prime of 0.682272 to get 2.396. We then divided both of those values and subtracted it from 0.682272 to give us our final answer of 0.682328, which is our closest approximation to the real solution.
This next problem is x squared minus 2x plus 1 is equal to sine of x. Before we do anything, we want to move the sine of x to the other side. So we end up getting x squared minus 2x plus 1 minus sine of x is equal to 0. As you can see, when we plug this into Desmos, we get 2 x-intercepts, but that only means that we're going to have to do the process from earlier 2 times. So first, we're going to calculate for the nearest x-intercept, which is 0.3862. When we plug this into Newton's method, we should get 0.3862 minus f of 0.3862 over f prime of 0.3862. Firstly, we are going to plug 0.3862 into f of x. We end up getting 5.1025 times 10 to the negative fourth. Then we're going to calculate for f prime of x, which is 2x minus 2 minus cosine of x. Then we're going to plug 0.3862 into f prime of x, and we end up getting negative 2.1539. Finally, we're going to put all these parts into Newton's method, and we end up getting 0.386436. Since this is really close to our initial approximation, we can just stick with this answer. Next, we're going to use our second x-intercept, which is 1.96. So when we plug this into Newton's method, we get 1.96 minus f of 1.96 over f prime of 1.96. Again, we're going to plug 1.96 into f of x, and we end up getting negative 0.0036. Next, we plug 1.96 into f prime of x and get 2.299. So we plug all of these parts into Newton's method, and we get 1.961566. But Tanvi, wait! Why is this important to teach in high school?
I'm glad you asked, Sheila. Linearization and Newton's method is important to teach in high school because it will prepare students for success in the real world in topics such as finance, physics, and engineering. Let's do one!
In finance, we can use Newton's method to find the yield to maturity rate on a bond. The yield to maturity rate is a calculation of how much an investor will receive from a bond if they hold the bond until it matures.
First, we use the market price equation, which is f of x equals c divided by x times 1 minus 1 plus x to the negative n plus f divided by 1 plus x to the n minus p. This equation solves for market price, and we're using it to find the yield to maturity rate, which is represented by the x variable. In this equation, p equals current market price, c equals annual coupon payment, f equals face value, x equals yield to maturity, and n equals number of years.
Then, all we need to do is find its derivative, and then plug it into the equation of Newton's method that we learned about earlier. Next, we make guesses consecutively until we reach a good approximation for the yield to maturity rate. Let's try it out.
So, you are thinking of investing in a 5-year bond with a face value of $1,000 and an annual coupon rate of 6%. The current market price of the bond is $950. What is the yield to maturity on the bond?
So in this question, P is equal to 950, which is the current market price, C is equal to 60, which is the annual coupon payment, F is equal to 1,000, which is the face value, and X is the yield to maturity rate, which is what we're looking for, and N is equal to 5. We can start by plugging in the given values into the market price equation.
F of x equals 60 over x times 1 minus 1 plus x to the negative fifth plus 1,000 over 1 plus x to the fifth minus 950. Then, when we graph this, we get an x-intercept of approximately 0.072.
Then we take the derivative of f of x, which is f prime of x is equal to negative 60 times 5 plus 4x over x squared, all times 1 plus x to the negative 6 minus 5,000 over 1 plus x to the 6th. Now, let's say our initial guess is 0.02, which is 7.2%. We just need to apply Newton's method consecutively, and we end up with 0.07161 after only one repetition, which is very close to the x-intercept of the graph.
This means that the maturity on the bond is 7.161%. If you hold your bond until maturity, you should expect a return of 7.161% annually.
So thank you so much for watching.
Tanvi
and Sheila.
Stay tuned for the next video!